Yes, it is visible.
Okay, so I'm starting then.
You go ahead, start. People will join.
Okay. Okay. So in my last talk, I have started doing the Kiteav model solution. I'm going to do a brief recap. So I consider a 2D lattice where all the uh, nearest neighbor interactions have different strengths. So there are Jx, Jy, and Jz, and they along if these are X link, these are Y link, and these are Z link. So if the two atoms are connected via X link, so their X components of spins are only interacting, and if they are connected via Y link, then it is considered that their only YY components are interacting, and that's for Z also. Okay, so for then consider the spin half case, then the SIX becomes simply my Pauli matrices, and then I defined operator by this where sigma 1z sigma 2x are defined like this. They are these links, the red links here, and for that operator bp comma h commutator is 0, so bp becomes my conserved quantity.
Ritika, so if you extend that picture, where will be the next placket?
Next bracket can be like this.
No, you define it, then there is overcounting. How do I define the, let's call it P prime. Will you call it P1, P2? What is the lattice structure in the placket language?
Placket language, it will be like that. So but there will be some over like for the next placket drawn by this green thing.
Why
What?
don't you write an operator for that?
Okay, okay, okay. Then if I name it like some 7, 8, 9, 10, and 3, 4. So they are uh, okay. So these are the links which will be there, and so the operator will be P Q will be equal to sigma sigma 7 Z sigma 8 X sigma 9 Y sigma 10 Z sigma 3 X sigma 2 Y.
But then my question is, if BP commutes with the Hamiltonian P being any placket,
Huh.
it stands to reason this should hold for an arbitrary P,
Huh.
right? So it should also, if A commutes with B and B commutes with C, then A also commutes with C, right?
Yeah, B and BP and BQ also converts. Yeah.
Can I see this quickly from here?
Um,
You can use the property of the polymatrices, that sigma square.
yeah.
That's why I made you draw. There are overlaps, right? So now
Yeah,
some of
yeah.
the sigmas will go away.
Yeah.
Can you
So
quickly
only
see what is the,
these two will be contributing.
yeah?
And then for sigma 3 3, if I calculate BQ commutator, so contribution from 3 and 3 commutator will be exactly opposite to 2 and 2 commutator. So that's why it will become 0.
Okay. But you should do this calculation and
Yeah, I have done
Okay.
this calculations. Um, okay, so then yeah,
Ritwika, so there is no placket interaction, right?
not placket interaction. So actually, what you can write like such Hamiltonians, this after some time I will show that this Hamiltonian will be Z2 gauge symmetric Hamiltonian. So then one can write any gauge symmetric Hamiltonian like sum of all the placket. Uh, so sum of all the placket. So actually yes, there will be no such interaction between plackets. That will be sum of all the plackets. One can write it like that.
No, but I don't understand that.
Oh,
Because in your original Hamiltonian you had some SI, right? So if you think of, you just take the first term of the Hamiltonian.
yeah.
So if it is S1, S2, this becomes sigma 1, sigma 2.
Hmm.
So let's say X.
Hmm.
Now, you just talked about BP, BQ commutation relations. So if you multiply BP and BQ appropriately with overlapping bonds, then clearly the overlap terms will survive, because now you are no longer taking a commutator. You are just trying to
Yeah.
the Hamiltonian in terms of.
Yeah.
So you shouldn't you be able to cast the Hamiltonian in terms of interactions between BPs and BQs, which are nearest neighbor to BPs?
Mm-hmm.
No, I don't know. I'm just asking. The structure allows it, but one has to do the algebra and see if it.
So this Hamiltonian, how it look like in terms of BP? Then one can get like a one-to-one correspondence between these two.
Actually, I don't.
You are going to show that, right? That how it will be.
I didn't. I will not show how it look like in terms of BP or BQ, because I don't I don't know how it will look in terms of this BP.
No, you can make it a no, because this anyway will be necessary for what you are trying to do in this problem. You are going to work on this, right?
Yeah.
So you should make a note how to write this low. This is much like the toric code model, okay?
Yeah.
With the toric code model, you can write a low placket Hamiltonian.
Yeah.
I suppose one should be able to write it. My question was more so: is it a low energy Hamiltonian, or is the exact? You recover the exact? Is the exact mapping? But you can multiply. Should be not very difficult, right? BP, the thing that you just wrote, BP BQ. Carefully see, you might end up getting even higher order terms. Okay, or you might have to introduce some BP BQ multiplied by some suitable sigmas to recover the Hamiltonian terms in H. Okay, it's an exercise. I don't know the answer, but this is an exercise you should sort of try to do.
Okay.
You are going to talk about the vertices becoming triangles or squares, right? Or no?
Vertices. Yeah, I will.
You are going to talk about that. No, I mean that is what you are supposed to do anyway.
Yeah. Okay. Yeah, I am going to say briefly, but not that much.
Okay, go ahead.
Yeah. So then, what I did is, I first that was my actual system, where each side there is two possibilities. If one is upspin, if one is downspin, then my Hilbert space for each side will be 2. Then I am casting this to another problem, that there I have two sides and I can fill it by any arbitrary number of fermions. So there will be 4 possible then states. One is empty, one is first one filled, one is second one filled, and one is both are filled. Okay, so then if I write it like in creation operator, then they will simply follow the anti-commutation relations. So this is basically extension of Hilbert space, and these operators are normal electron creation annihilation operator, normal fermion creation annihilation operator. Okay, so then I am introducing my Majorana operators. It looks like that. So where these are the
generally what you are saying is fine, but especially because you have made a note and brought it, your indices have to be kept. All the indices are sort of confusing here, isn't it? The IJ belongs to the internal space, and the lower Majorana don't have any indices at all. how are we going to understand the indices?
Okay.
No, when you write a note, I mean, especially, I mean, if you are, asked to do on the blackboard, sometimes you might miss. But if
Okay.
you are bringing a note, you should have the indices properly written. Or you should say about what is this INJ index? Are they physical site indices?
I and J. Yeah, they are site indices.
Site indices? No, that's
Yeah,
not.
this.
How is it site index? I'm sorry. This up and down refers to a single site. What do you mean? Then C1, C2 belongs to cannot be on different sites, right?
C1, C2 is on single site. Yeah, C1,
So
C2 is
what is the label of the site? And what is the 1, 2 label pertaining to?
C1, C2. C1 is basically say up spin and C2 is basically say down spin. It is like that.
No, it is like that. If you give this as a lecture, the students will walk out of the class. Okay, so let's be serious about it. Okay, I mean, you have this notion of being a bit cavalier with notations. Slow down and be a bit pedantic. This is for your own good.
Okay.
Okay, slow down.
Okay. So,
Okay, so you carefully explain what is 1, 2, IJ before you proceed any further.
okay. So, C1 dagger is basically here I consider two states. So one state I labeled as 1, the second state I labeled as 2, and creation of that one state is I considered as C1 dagger. So actually this relation will become C1. I actually wanted to write C1 dagger this is equal to 1, and other C1 comma C2 dagger is equal to 0. Then all other possibilities say they are also equal to 0.
You have to still retain the index I
Yeah.
site somewhere.
And this is for site I say. So then
Don't use a capital index for the real space sites because you have small indices written in your commutation.
small. Okay. So
Just call it capital I, the index for the site. Just call it. So then you put a subscript or superscript I somewhere in the C's and everything will be fine.
okay. So this is for single site. This is 0, and then I reconsidered my this C1 C2 operators written like this. Or
No, now slow down. Now what is the I on the left hand side?
I on the left hand side is my site.
Okay.
These are capitalized all.
So if you are teaching like this, it will be a disaster. And especially for jobs and postdoc, they ask you to give examples of teaching. You cannot do this. By this time, people will say, this person doesn't have a good board work. Let's move to the next candidate. So please, next time onwards, don't make this mistake. You're bringing a note. You should, even if you know in your head, you should know how to write on how to present your work. Okay, so how will you teach anything in your life?
Okay. Okay. So then I
What's
just
the alpha here in this?
alpha is my this XYZs.
Okay.
XYZs. I have from now on I will use my XYZ as general index as alpha, beta, gamma in general, and IJ will be my side indices.
And if you want to write the internal indices, you will explicitly call them 1, 2?
1, 2, yeah.
Okay, go ahead.
Okay. So then
Ritwika, one minute. This capital I is your site index for the Majumdar, right?
site index for the Majumdar, yeah. Capital I is site index for this one also. My this 1, 2 states. For that also, I am considering.
This is the lattice site for the spin, isn't it?
Lattice site for the spins, yeah.
I mean, that is the physical quantity. You are expressing it as Majorana. That's a separate.
So let me try to understand this point. So it means that each side, so I can easily write that C1 dagger, it is will like a C1I dagger, right?
Yeah, yes,
So,
yes, sir.
and C2 dagger means C2I dagger. So on that side, I can create upspin and downspin.
Yes, sir. Yes.
Am I right?
Yes, sir. Yes, sir.
Okay. Then I have it. Yeah.
Yes, sir. Okay. So then from C1 and C2, I give this algebraic. I give this algebraic formulas for this. They are my Marana operators. Why I am calling Marana operators? Because they follow these rules. The ck square is equal to I, and ck alpha dagger is equal to ck alpha, and ck dagger is equal to ck. They are self conjugate of each other, and they are two operator acting on same state is equal to identity.
I want to ask
Yeah.
another question.
Okay.
So this operator, how those relations will differ from your fermionic operator? Means the C1, C2.
For my fermionic operator, my C1 dagger is not equal to C1. Here,
Yeah.
that is first one, and then the second one is C1 into C1 is not equal to I. Their C1 dagger is equal to I.
Uh-huh. Yeah.
Okay. Uh, okay. So so they will follow this anti-commutation rule. This is general. Because they are two different sides, so they will anyway anti-commute. And okay, so then the relation between C and Cx is this anti-commutative relations are not uh, not known. Okay, for now. Then
What commutation relations are not known?
this C comma Cx anti-commutation or commutation.
Why am I looking at only that commutation relation? I could construct many commutation relations
Yeah.
or commutation relations. What's so special about this particular relation?
There is.
No, I mean, I don't. No, I'm trying to understand. You have already defined the Cx in terms of C1 and C2, right?
Yes.
So you stick it in here, you'll get an answer. What do you mean not known? You'll get an
Yeah.
answer. So
Yeah, I can get an answer.
no. So what is known? I'm trying to understand. What do you mean by not known? Not known in what sense? You have,
I have not written here. That's why.
no, you have not written that separate issue. I mean, is there ambiguity
No.
in the commutator?
No.
Commutator?
No.
Okay.
So then I am defining my interaction spin operators in terms of this Marana fermions like this. So if I define it like this, they are satisfying my normal commutation relation of Pauli matrices and also the anti-commutation relations, and they have this commutation relation also. From here, one can prove, I have proved separately that these are the two commutation relations that the Marana fermions hold. Okay, so up to that, no, then I defined this condition. Then up to that, I have done in my previous talk. Okay, so then
This is another point. This defining sigma kx equal to I ck ck. So what does it mean? So ck is the full. I'm not getting this one. Ck is what? Then you are defining ckx. I can understand there. And then ckx. What is the difference between ckx and ck?
these are these are the relations that become messy.
No, Ritika, why don't you just demonstrate CKX? CK says show that it gives sigma x. Okay, can you just quickly do the algebra?
Yes.
Just do a demonstration. Do on a clean page. You're sort of messing it up. Do on a clean page. Just show that.
And then show the.
Just for one matrix, it should be accurate.
Okay. My C is equal to C1 plus C1 dagger. Okay, so sigma Uh, I am supposed to show from here that sigma x is coming.
You yourself said that if that is the definition, the commutation relation satisfied, right? So
Yeah.
then what do you mean by that? So when you say an operator is equal to another operator, what does it mean? When you, the question that you are being asked to show means what? You have to show an operator identity, right? You have some on the left
Yeah.
who's in the worst case you can think of it as a matrix.
Oh,
You can show the matrix elements element by element they match. Can you? That is the simplest way. You could show it in a more formal way, I suppose. But the simpler, you don't have to show commutators. You know what the sigma x matrix is. Can you show that the right side appropriately gives you the sigma x matrix?
a little go up, maybe I can understand. One moment. Okay.
You have to choose the basis properly. See, this is. I mean.
Okay, I got it.
No,
So
but
basically,
it's not so trivial. The point is your sigma x that you have, for example, is a matrix in a chosen basis where sigma z is your diagonal object. Now, what is the basis in? If you sandwich it in the same basis, you need to know what is the action of these CKs on the up and down. So, for example, if you take the up expectation of sigma x, you will get 0, right? That's the diagonal component, top down. So, can you calculate what is the? You can perhaps at least show that much. What is C dagger? CX K CK acting on the upspin?
Okay. Actually, this C1 is not exactly equivalent to C up. Okay.
Right. That's the point. That is why it's asked.
Yeah. That is actually a linear combination of C up and.
So no, you're not understanding. Of course. So this is a matter of principle. If you have you have a relation, right? You know what CK is in terms of C up and C down. Yes, no.
No.
You know, don't know.
No, I don't know.
What is C up? C dagger up क्या करता है?
C up dagger that will create a upspin on vacuum.
So then how? Then the original mapping you have not understood. The original mapping, you go to the top. This is the trouble. You guys want to do fancy stuff and you get stuck in. First, you are not careful about the initial problem. Now, how do I relate the up with these things? So what is the correct basis to choose? Because you have now defined new operators on the right hand side. The left hand side operators were in terms of the spin operators. There was no C daggers. Okay, so the spin operators for half spin, let's say you do a two-dimensional representation, will give you up down as the basis. That's the left. You have mapped up to a state, down to a state, and so on and so forth. Okay. Now you have to use when you're taking the superposition, the expectation value to expectation of sigma x, for example, between up. Okay, you have to then on the right hand side do the equivalent, take the equivalent states of the mapping and then.
Yes.
I mean that's what you have to do. I mean there's no sense in saying C dagger is equal to. There is no C dagger. See, first of all you have to understand in the problem you are doing this particular problem there is no electronic C dagger up or C dagger down. You of course I believe know that a C dagger sigma is a fermion. S spin operator is not a fermion or a boson.
Yes.
You know that?
Yeah.
Why? Why is a spin operator not a fermion or a boson?
That is basically a operator. So I can.
So everything C dagger is also operator, spin is also operator.
C dagger is a creation operator.
Yes.
Of sites and spin operator.
I mean, I could write
at a
in arbitrary space.
Yeah.
Commutation relation per se is nothing to do with. I could use the I as anything. The answer is there, right? You've written its answer right. The first blue line in the slide. What is the commutation relation between the two sigma matrices? It's not commutator or anti-commutator, isn't it?
No. Mm.
Neither boson nor fermion. It's kind of trivial, right? It's written there.
Mm.
Your answer.
Yeah.
Okay, so spins are not neither.
Yeah.
Okay, but you have now taken a spin and mapped it onto a fermion.
Hmm.
By enlarge, you cannot just do that. So you have to enlarge the Hilbert space. Otherwise, this mapping becomes tricky to do. You've done this mapping. So now if somebody comes along and asks you, hey, if the left-hand side was a Pauli matrix, in what sense is the right-hand side equal to left-hand side? Are you saying the matrix becomes the same? Are you saying the algebra remains the same?
Algebra remains the same.
The matrix representation is a trickier thing to show, which I was originally suggesting, because you have to appropriately choose a basis.
Basis, yeah.
Okay. But all you are saying is, suppose I do a mapping of an operator sigma x into a product of two operators suitably chosen as C dagger, CXK and CK, then it can be shown that the relations between these C operators are such that it preserves the commutation relations of the sigmas. In that, by that logic, it's a map.
Yes.
By that, it's a what in a standard terminology, this is a canonical transformation, because it's preserving your anti-commutation relations. Beyond that, to make a matrix, it's a trickier game. It's not so. Okay, so the answer to what Ashish was asking is that you have simply used a mapping that preserves you have just done a canonical transformation. Okay, that is all you have done. Whether it essentially means something is a very what does the C's individually mean in terms of the spins? It's a much harder thing to say. I believe at the moment you have not brought in any constraints.
No, up till now, no.
Yes. Okay.
Okay.
Okay, see, Ashish, does it answer the question you are asking?
Yeah, so somewhat, yeah.
But it's not a matrix going to a matrix. It's an operator going to a different product of two operators, such that the commutation relation of the left becomes the commutation relation of the right. The C. So it's just a construction at the moment.
Okay, yeah. I got it.
Ritwika? So I don't know. So I actually last time I also wanted to understand the transformation of the mapping. So as Anamitra was saying, is it like suppose considering if you have a single spin, so it's like when you have a spin, then it can be like in upstate or downstate, right? But you don't consider if you consider it as an electronic spin, so then there's a different way of looking at it, that if there is a site thing, that either the site can be occupied or unoccupied.
Yes.
And if it is occupied, then there can be up or down state. So there are four possibilities with a single site. Either it would be not occupied. If it is occupied, then either it's up or down or up down. So that's one way of looking at it. The other guy is that you already have a spin, and that's the spin only you're talking about. You are not talking about whether the spin is there or not. The spin is there. It can have only two states. Are you talking about that kind of mapping? So if you think of the top left corner, when you said that there's up and down, does that mean that that kind of state is like we have a spin and it is there, and the other picture is like we also club with it the side thing, that there can be an unoccupied state and occupied state and unoccupied state. So is it like that kind of mapping?
Yeah, that's why it is the extended. If you consider this as can be unoccupied and occupied, then there will be four possibilities, right?
Exactly.
So yeah, so that is not the case here. That is, I have a spin inside that can be up or down. Then I am mapping it to 2 to 4 state mapping. That's why my Hilbert space is getting extended.
So I think what Anamitra said, I kind of probably can relate to that, because the first thing is that you are not considering any occupation. So it's probably the first thing is not occupation number basis. It's just you have a spin, you have two states. Either it can be up or it can be down.
Yes.
So that's one kind of Hilbert space, single particle Hilbert. Then you are mapping, then you are going into occupation number
Space.
situation.
Yeah.
So where you are, so then your left side, that is this, so there are two stacks, right? So first stack represents to what?
This one, this line. This one, first one is up spin. This is up spin.
No, not the left, the right hand representation.
This.
So there are two stacks, right? One is like, so you wrote it like minus, minus, plus, plus. So minus minus means what?
Minus means unoccupied. That is the empty states.
Okay, but when you said plus minus,
Actually this is not plus. There is one and there is nothing. There is nothing. There is one. It is like that.
Okay, so two
No,
states.
Swagatam, let me sort of clarify. So, I mean, this is just a mapping. Okay, a mapping, just as I don't know if any of you were in yesterday's talk by this Kallol, the postdoc that's going to join the, he was doing a mapping. Okay, so you take a spin problem, you map it onto bosons. Here you are mapping it onto a set of fermions. The reason you have to, at least as so far as I understand, you require 2 degrees of freedom as C dagger 1, C dagger 2, because you need to make sure that the spin algebra remains preserved. So you need to introduce 2 degrees of freedom. But having introduced 2 degrees of freedom, you are then forced to have a Hilbert space which has 2 sort of placeholders for their occupation and deoccupation. This 1 and 2 has nothing to do with sites. This is an internal occupation within the Hilbert space that you've attached to the site I. 1 and 2 has nothing to do with the sort of real space hopping. Real space mein there is a spin which can be up and down. Its states are mapped into a state of Hilbert space. There are 4 of them because you are forced to use 2 operators to sort of fix, to ensure that the spin algebra is preserved. And in terms of those states, you can have occupation, deoccupation, just as in a slave rotor you have a single electron on a side. Okay, and the electron can be split into F dagger e to the power I theta. The e to the power I theta is because it's LZ angular momentum. This thing, so U1 U1 variable, it can have arbitrary value. So you can worry about एक electron था वो infinite कैसे हो गया? That's because that is infinite only because you have not yet put the constraint. In the same way, but those excitations of the rotor has nothing to do with electron hopping in space. All of them is at a single site. The entire mapping at a okay. So nothing is jumping in or out. So that's the thing. And so far as your the Hilbert space of the fermions on the right hand side, the C daggers is concerned, it's clearly a larger Hilbert space. There is hopping, but this hopping is in the internal indices.
It's that thing. But you have to map. How do you map it back? So ultimately,
so see, this mapping back is not. So that's not how this is constructed. The way this. So you can think of it this way. For example, in the bottom red corner, the 3 relations that are written in red, the left, that one, left. Imagine I had given you a theory with the C's, and then you came up with a combination of the C's which you call sigma and said that C ka kuch anti-commutation tha, algebra tha, sigma is following that. So it's just a construction. So given a spin, you have written it in terms of 2 different products of operators, and you have imposed properties on those operators such that you ensure that the spin algebra remains preserved. Okay, so generally these are, I mean, in a strict mathematical language, this is a construction. You start with some algebra known for the spins, then I'm sure, I mean, because these Kiteav etc. wanted to bring in the Majumdar representation, They said, let's try with Maran, and then we basically have to make sure you put a lot of parameters and then set other things and make sure that they can be set 0, some things can be cancelled, such that the relation is preserved. So these are all by construction. I mean, the reason Kiteav model is famous is because it's solvable, right? Now, if you just do a random mapping, it will not be solvable. So it requires somebody like Kiteav to, so there's a lot of hard work to make sure what is the correct mapping.
So actually, it means that because it's a spin-only problem, I guess. So there is no hopping to begin with. So that's why we don't need to consider the occupation and deoccupation on real site.
No, I mean, again, there are different kinds of mapping. This is a single site mapping so far.
So what I'm saying is that in real space, if you had an electron moving around here, to begin with, the Hamiltonian has only, we are considering a spin Hamiltonian.
Yeah, but you don't have to have electrons for things to move around, right? Think of a
spin.
Exactly. For a spin model, if you create a single in a ferromagnetic background as an example, you can create a spin flip. That's a one magnon excitation, and that one magnon excitation can move through the lattice. And so you can have kinetic energy for the magnons. Okay, or there could be other excitations like in yesterday's, you can have zero magnon protected excitations.
But Anamika, I think the hopping will not come because it's a spin only model. So whatever the hopping can actually lie in your J, whatever the excess.
But then this is a question of the spins are still not hopping, right? Spins are still physically present there. It's some complicated excitation of the spins. So there are two things one should differentiate, I suppose. One is the mapping itself. That is done much like in a slave rotor on a single site. That's the story. But then suppose you have a two-site problem, just to give an example. Now in the two-site problem, which Shubhajyoti can add on a two-site problem, you can have internal rotor excitations. Okay. But that necessarily does not mean something is physically moving. Okay, it may or may not mean physically moving or something which an excitation can move in the system. Okay, so it's basically saying two spins are sitting on two sides. You can have, if you allow a J between the two spin, you can get a singlet and triplet. Now the singlet and triplet can be thought of as spins fluctuating between on the two sides individually. But the collective state lives on the two-side problem. It doesn't live on the left or the right separately, isn't it? It's an entangled state. Right? Yes, Swagatam.
Oh, I thought you were asking.
No, it's simply on a single side you can define a mapping. That's what she is doing. And then when you bring different sides, things will move, but those things are not the spins. Some excitation of the system, just magnon being one simple example of that, can move through the lattice. Okay, but actually, not the spins themselves.
What I think is that if you just think one term of the Hamiltonian, suppose SI/SJ with X-link or Y-link, whatever, the Heisenberg type, that is written in the basis, that the top left corner thing. No, on the same page. That is written with this top left basis, right? The two-state basis.
Yes.
If you could have written that thing in the right-hand side basis, then probably.
What is the right-hand side basis? I'm sorry.
The mapped one. So
see, that's the point. Swagatam, we are not getting the point. It is not easy to do. See, you have to understand what a construction means. Construction here is not a very trivial word. It has a specific mathematical meaning. A mathematical construction takes you from one space to another space as a mapping, which is an explicit construction. Construction what does that word here mean? It means that whatever properties of your left space was, some properties, whatever you want to make it survive as a general sense, that construction, you create terms by hand. That takes you to the answer, what you want. Okay, writing a reverse mapping is very difficult because in this mapping, what she has done so far, there is a constant she has not talked about. So this is the right hand side, there are physical and unphysical states. You cannot go back. There is no, this is not a mapping in the sense of a one-to-one mapping between states. You are enlarging the space, so this is a non-unique problem. You cannot map back. It's not possible.
But can we write the Hamiltonian in this map?
No.
Or
until unless you put the constraints, you should not. Even if you, you can. You all keep the slave rotor in mind.
okay.
The slave rotor, you can write the Hamiltonian in the slave rotor representation, of course. But then that is not the correct Hamiltonian, because you are living in a enlarged space where there are unphysical states. So until you have a way to put in the constants exactly, not on an average as Shubhajyoti has been doing, exactly. This statement is, even the reverse mapping is an approximate statement. And it's very difficult to write. You can do it. If you have some time, at some point I can tell you how to construct. You have to construct some operators which commute with the Hamiltonian, but classifies physical states with one eigenvalue and unphysical states with another eigenvalue. You can do that. That cannot be for 2 sides, 4 sides people have done, and there are papers people have written on this. Okay, but in general, it's not possible to do this. Okay, Ritwika, move on then.
Okay. Then then the first condition that I have imposed in my last talk, that is this Pauli matrices will follow this simple relation that sigma ix, sigma y, sigma iz product is equal to I into identity, say. Okay. So but if from this construction, if I calculate this sigma x, sigma y, sigma z, that comes as cx, cy, cz into c. The operator forms like this, and that can be in this C1 C2 space, that can be written like this. Okay, 2n1 2n minus 1 into 2n2 minus 1 into I. So basically in this map,
Ritwika, you're still on the single site.
Yeah, single site. This ith site. This
P is the ith site, right? So all of them is at the I.
Yeah, all are i's. Okay. So then this D becomes I for these 2 states and becomes minus I in these 2 states. In that sense, I can say that these 2 states are physical and these 2 states are unphysical. Okay, that is where I stopped yesterday. So then, yeah.
So physical and physical, can I just one moment? This is giving okay. Di equal to I. Okay. So this n1, n2 are those with the number on the
in this space.
Yes. Okay. Okay. One moment, just n1 equal to, so which means that n1 equal to 0 is 0, then this is I, and this is 1, this is I, otherwise it will be minus I. But why say that minus I is unphysical?
Minus I, because my sigma x, sigma y, sigma z should follow for a Pauli matrix. They should
okay, I got it. Okay. Yeah.
Okay, so now I will move on.
So just a comment. So pertaining to the discussion we were just having prior to you bringing this out. So Ritwika, you notice that this is exactly the kind of operator that I was just talking in replying to.
Yeah.
This is an operator which clearly will commute with the Hamiltonian. It has to, I hope, or does it? Or at least, okay, so let's bring that issue. That's I'm not sure that commute, but nonetheless, this is an operator by which you can separate between physical and unphysical states.
Okay, so another point I want to ask that this you define di equal to sigma x, and now this 2n minus 1, that is actually how, because of the definition you put it earlier.
No. Yeah, actually, sigma mathematical. I'm saying that sigma x, sigma y, sigma z. I write it in this language first, then it comes in this form. Then
then you put it that C1, C2.
Yes,
Yeah,
yes.
yeah, okay, got it. And this basically N1 is nothing but C1 dagger C1.
N1, yes, actually.
Yeah, yeah. Okay, it's a two-step is there actually inside. Okay, yeah, got it. Yes.
So, okay. So, this was my construction. Then
So Ritika, just make a note. I mean, this is for future. We should check the commutation relation between the D and the Hamiltonian.
D or Hamiltonian actually commutes, and that's why the projection. From here, I will define the projection from one Hilbert space to another.
Yeah, but wait. If D and one has to be a bit careful. The Hamiltonian is not a local operator, right? The Hamiltonian.
Yeah. So
the way you listen to the Ritika,
okay.
Listen to the point before you reply.
Sorry.
The D is a local operator. Okay, now this Hilbert space of physical and unphysical that you have defined is a local statement at the moment. Right? This 0011 is only pertaining to a site.
Site, yeah.
Isn't that's a local statement?
Yes.
The Hamiltonian, if it acts on this, if the Hamiltonian, imagine that you write the Hamiltonian as Shwagatam was saying in terms of the C and the Cx and the C's, then this will map it into something. And moreover, it's even worse because the Hamiltonian has I coupling to J sites.
Yes.
So it will create states which are very different than the simple 0011 kind of looking states. The formal, see, that is why I was worrying about this. If the Hamiltonian commutes with D, you are saying it's true, we'll discuss that later, but if it's very important, it does, because then the entire spectrum of the Hamiltonian will also diagonalize D, which is not apparent from the statement you have written. This statement that you have written is for a single site.
Yes.
Okay, this is not to say that the states of the Hamiltonian diagonalize D, but if D indeed commutes with the Hamiltonian, then it should, right? That's the property, that's why we look at commutators.
Yeah.
And then the second thing here, what one has to show is that indeed, for any general state of the Hamiltonian, if D acts on it, then it will still classify physical and unphysical states. All this is not yet shown here. This is just a single. You have shown this at a single site, but clearly on a single site your Hamiltonian is 0, so it's trivial. Okay, so that is a point technical point we should clarify.
Okay.
Yeah, I have a question. Here you have the i's di. That's I at the side, right?
Index, yeah.
Okay. Now this N1 is Ci dagger Ci. Then what is N2?
Ci, N1. These are all at site I say. That is C1 dagger C1 at both are site I. It is like that.
Okay. And in the page before it, in the left hand side, the red color, you have written sigma k. Okay, so that's in the this is in the different space, right? The case
K is also position. That is
okay.
I. That is just
Okay.
Hello, Ritwika.
Yes.
So you have restricted the space. Now you have only two basis state. So now if we calculate that thing sigma xk and sigma ky, that will come equal to Pauli matrices.
Sigma.
If I calculate sigma x, let's say in this basis, the restricted basis, so that will be equal to Pauli matrices, right?
Yeah, it
From that operator, I, ck, x, ck.
No, Prabhakar, no. That's what we were discussing. It will preserve the algebra. So again, an algebra does not necessarily mean representation. Right? In a group theory, if you have the polymet, see, normally we are all taught spins like polymet, those matrices for half spin, right? That's what you are in. But if you think not in that language, but think from the group theory point of view, there is a group, and the group is a set of symmetry transformation that leaves the states invariant. okay, which satisfy the usual properties of group. Then Lee came along and said that, well, in certain kind of groups, you don't have to look at the full group, you can just look at local infinitesimal transformations which generate the algebra. Like translation in real space of 1 meter can be broken down into 1 centimeter or 1 millimeter and so on and so forth. So all the properties of the group can be faithfully reproduced provided there is a unique algebra for a given group. Okay, so that's the story of the algebra. Now what she is saying is that I have a algebra for the spin polymatrices which is well known, SU2 algebra. That's the usual algebra. Now she is constructing operators, product of two operators, saying that this algebra is preserved. Okay. What it does not tell me is are they as the matrices they are preserved. It does not tell you. For example, as she will later perhaps show, I don't know today or maybe sometimes later, I will run out of time. Maybe later when she understands the later part. See the algebra being for SU2 being same under a mapping does not mean that the representation has to be of the same dimension. SU2 can have many dimensions in terms of representation, the minimum being 2. So it could be a 2-dimensional representation being mapped onto some higher dimensional representation. So the representations may be completely different. That's why when Ashish was asking this question, I started, but then I realized it's not so trivial to do that. It's tricky. One has to make sure because you have to know the action of the CKs on the spin basis.
Yes.
That is not known. The moment she has defined some notion of operator going to operator, to get a representation, you need to know the action of the operators on the relevant states. Okay, so that is what she has to construct now. See, even in this D, for example, you could say, how did she write that? So the trick, still she has done the same thing, that she wrote in terms of sigma, but she did not apply that on the sigma itself. The trick was she converted into the C's and then acted on the 0011 basis. And she could have done, and she had done this on the first line. She has done the calculation in the older basis. That is, if you take the spin matrices and the spin basis, then the top line will work out. But to get the second line, you have to know the action of states on basis. So she first wrote the sigma. She did not act 0011 on the sigma because that action is not known directly. So you cast everything in terms of the C's and then do the action. But clearly left hand side ka space is 2 cross 2, is a product of 2 cross 2 matrices. Na upar wala lines. Niche wala could be a bigger matrix. But it will still satisfy the same algebra. Okay, so representation is preserving the algebra but not the matrices.
Okay.
Okay, Ritwika.
Okay, so then I am writing say one part of the Hamiltonian, say x part of the Hamiltonian. It is jx sigma xi sigma xj. Yes. So I will write sigma x I and sigma xj in terms of Majumdar operators. Okay. That will become jx I cix ci I c jx cj. So then I will so they are specifically in different sites, so they will anti-commute anyway. So jx into I cix in jx into I ci cj. Okay, I have written it like this. So now I will define my uijx is like I cix cjx. So then one can show that uijx is commuting with my Hamiltonian. Okay, if I write this Hamiltonian in the total Hamiltonian in this C basis, so then it will my U I J X will commute with H. And
Ritika, sorry, just maybe so I'm just repeating.
yeah,
So you just I completely missed. I was probably thinking something else. So you are calling this is UIJs because these will play the role of mean field theory. That's why I'm
yeah.
just
That will be the auxiliary field.
so okay. So let's just pause a second. So you're saying you're writing it back in the C notation, which is Shagatam, what Shagatam wanted anyway. So then you are defining CX. I see. CIJ. No. Maybe this. I mean, you will do the Haber-Stratovich here, or
No.
no? So then, but why can't I choose the CXI CI? But that will be trivial, right? If I take CXI CI
See,
itself as the mean field order parameter,
this will not commute with H.
that's okay. I'll solve it numerically. It's still a one-body problem.
Okay. Then actually, so if I consider this, and then another one will be left for my CJ. Okay.
No, it might not be exactly solvable. Kiteav model is exactly solvable, right? So under this, because see, if you are going to do a mean field decomposition, there are four operators, right? CXI, CXJ, and so on and so forth.
Yeah.
Oh no, does it vanish? CXI, CI expectation, does it vanish? No, it cannot vanish, right? Because the left hand, it is identically equal to I times sigma x. It cannot vanish, right? Then the Hamiltonian will become 0, I guess. No.
So from here, why I defined it, let me say, so that becomes like this is my what is my CI is one Majorana, CIX is another Majorana. I have 4 Majoranas, right?
Yes.
For each side.
Yes.
So I am coupling this X and X. So then, if when X linked, say this is this is my so this is my X link, say. So these two are connected. I and J, my I and J is connected by X link, and that is defined by this. So along this bond, the UIJ is my conserved. So this IJ, this becomes say CI to CI to CJ hopping, not CI to CIX hopping.
Sorry, what? CI to CJ hopping, CIX to C.
Like this CI CJ is like CI going to CJ, right? CI and CIX are different.
No, that's okay. I mean, you can think because creation is annihilation. I can think of that is C dagger I CJ. Will mean the same thing, right? Because creation is annihilation.
Yes.
Okay, so I can think of that as a hopping term. C dagger I CJ.
Yes.
As a hopping now in space. Unlike the internal indices that we were talking about so far.
That is IJ are real lattice space.
Okay, now slow down. There is a conceptual issue here. Where is this? So now if we, so you are saying that I define. Well, I don't know if does Wick's theorem hold for Majorana's? I don't know. Fermions it does. I don't know. Maybe Kushi's now. You would probably know. Do you know, Ritwika? I mean,
No.
because I mean, if you are doing a Wick contraction, which you could do for normal fermions, I presume you can do it for Majorana because at least quantum field theory in the Weil representation or the Majorana representation still works, right? So it doesn't.
Yeah.
So Wick's theorem perhaps is still applicable. Let's assume so. So then you are doing a Wick contraction of two indices, which is the mean field. Right. So my question was, why don't I pair sort of contract CXI and CI itself? But perhaps that is a bit like the fully contracted term. You will subtract a term which is the left expectation and the right expectation, if I use that word loosely.
Then if you contract means I and I, then it becomes like the my Hamiltonian, the interaction information getting lost, right?
No, I mean it doesn't, right? Because it's like the Ni. Think of it. If there is an interaction term for fermions, Ni, N1, N2, N being number operator,
Yeah.
or Ni, Nj,
Yeah.
I can take an expectation of Ni,
Hmm.
but then Ni expectation acts as a field on Nj operator.
Hmm.
So there's still it doesn't break the interaction. It just makes it mean fieldish.
Mean fieldish. Yeah.
Okay. This I don't know the answer, so maybe I should not waste people's time. I should look this up as to why this is the only interesting decoupling.
Okay.
But you are saying that having done this, you can construct a operator order parameter U which
Concept.
commutes with the Hamiltonian.
So I am getting some extra conserved quantities other than placket operators.
Yes, that is true. Yes.
So that's why here it is done like this. So it is true for yes.
No, go ahead.
Okay.
I don't.
So it is true for all x, y, and z. So my all u, I, j, alpha is going to commute with my Hamiltonian, and also my u, I, j, alpha, comma u, I, j, beta, they also commutes. Okay. So then my Hamiltonian, the actual Hamiltonian that I had, x mean jx I. So okay. So there I have exchanged this, so there will be a minus sign. Sorry. Okay. So minus I dx dix c jx ci cj plus j. So this if I replace it like in by u I j, then it becomes like sum over all I j's where I j's are adjacent sides, then c I in bracket minus jx u x I j. Yeah, there is a minus I j y u y I j minus I j z u I j z c j. So as my u I j y and z, these three are conserved quantities for
Ritwika, slow down one.
yes.
Won't there be double counting here? Because now you are rewriting the Hamiltonian.
Yeah, there will be a double counting. So for that there will be a factor of half.
Yeah, maybe you should explain for the other students what I mean. You have done something from the previous step to the. You have recast the Hamiltonian by summing over nearest neighbor sites or something like that.
Yeah.
Maybe
So
just said that, but you sort of expand on it a bit.
okay. So I just write this as u x I j. First I did that, and then my these are connected via x links, y links, and z links. So each bond now think in terms of bonds, say. So each bonds are shared by two particles I and j. So if I sum over all the links clubbed together, then my sum is over I and j, where I and j adjacent, but each side have half of the contribution to the bonds. So that's why there will be a half factor. That half factor is considered inside this. Okay. Anyone has any question?
Yeah, Ritika.
Yes, yes.
So yeah, you said there are four kinds of Maranas, right?
Yeah, four kinds of
CI,
Maharanas.
CX, YZ,
Yeah,
and all.
yeah, yeah.
So you are when you are writing the thing, so
Hmm.
the term, the JX term, that can be thought of as a like a scattering term, like IJP, do Marana like destroy हो and the other two Marans get kind of created at IJ, the sorry JMA. Can be
Hmm.
thought
Yeah,
like that because
yeah,
they have.
yeah, 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 yeah.
And so, why are you somehow choosing the IJ? I mean, so the C type Majorana, you are separating it out in every case,
Hmm.
and you're clubbing X and Y's and
Hmm.
Z's.
Hmm.
So, what is the reason for to do that?
Uh, so say if I have constructed my ICJ as my UIJs, so
Mhm.
that will also become commute. Uh, no, that will
That
that
is
will
what
not
I'm
commute.
asking. Why
No,
you are not?
then it will not commute because my JX, JY, JZs are different.
No,
So
this is just a construction. Again, a construction. I mean, this is like, Kiteav started with a wish list कि ये करूँगा उसके बाद ये करूँगा, and to his wonder, I believe all of them fell in place. Generally ऐसा होता नहीं है. Things break down, but Kiteav or Halden could come up with this kind of things.
So, is it like, I mean, I don't know, you are going to, I mean, I felt like if there are four kinds of Maranas,
hmm.
Sagatam, I
Uh-huh.
just wanted to, the four kind of Myrana or four operator of Myrana, because
Huh.
what do you mean by four kind of Myrana? So they are different by nature, or
So Ritika, why
I
don't
just,
you quickly repeat what are the four Maharana modes that you're talking about?
I just meant four Marana modes, that's four kinds of, I shouldn't say.
No, but what are the four modes? Just write it down for completeness.
CI, CIX, CIY, and CIZ.
no, that I understand. This is good, but so this mode, can you physically define those modes, or what those modes actually?
No, everything, this is actually
Nothing is everything
internal,
is done
internal in
physically.
the mathematical
But
world. I don't think directly it means anything physically.
Actually,
can you show me the definition once? The four things, the definition of the four things.
four means
Not definition, the whatever that when you constructed it.
No, I thought this is the four kind of operator you defined for the Myrana.
Yeah.
Okay.
No, but those are Maharana operators, right?
Myrana operators, yeah. So those are Myrana operators, but that doesn't mean those are four different Myrana.
No, I mean those are four different. So different here means simply you can. I mean different, to make anything different, you need to have labels, right? So if the labels are distinct, then we can. I mean that is in the same spin that up and down spins. Although electrons are indistinguishable, I can still distinguish between up and down electrons by the spin quantum number. So here there are quantum numbers which allow me to differentiate between these four states. I mean, when they act on states and create something, I believe they will because they will generate
No, that I
with different quantum numbers, and so that will
particular nature of that Myrana, that when it acts on some state and then something will come up.
So Ritika, which one was the C? The first one, I see a Z. There.
C. Yeah, first one. This.
First one is C, and the last three is X, Y, Z, right?
Yeah.
Yeah. So that's again. So why are you clubbing? It's just a choice, or you?
Like clubbing like this.
So this is how Maranas are defined. So
No, not here. In the last page, scroll
to
down.
create conserved quantities.
That's what makes. So you are separating C only C's and clubbing X and Y.
The direction that this X dependent, Y dependent, these things I am clubbing together.
Because those generate conserved quantities.
Yeah. those generate conserved quantities. And
Because so more formally, when you want to make a problem exactly solvable, you have to ensure there are enough number of conserved quantities or constant integrals of motion. Otherwise, you will not be able to solve it. Right? I mean, you require as many degrees of freedom as conserved quantities. This is a statement about integrability. So, Kiteav probably had this, I mean, notion that he wanted to make sure that at every state the number of degrees of freedom and the number of constant of motions remain balanced, so that you can solve the problem exactly. So just like you can solve the Bethe answers, I mean, you can solve it because the velocities, crudely speaking, in 1D, the elastic collisions, if you start with n particles having velocities distribution, the velocities never change because they're elastic. They can get redistributed, but the velocities, set of velocities don't change. Because there are as many number of particles, as many velocities, and they don't change, they are conserved quantities. And that is what allows you, this Bethe answered solution comes from this set of conserved quantities. So in a similar way, you constructed conserved quantities that will allow her to solve the problem exactly.
So it means that CICJ doesn't commute with Hamiltonian when UIJ alpha does.
Correct.
Okay. So that's the thing. Thank you.
okay. So this is for the pictorial representation. You can think of like that. And this bond, along this bond, my UIJX is there, and that is a conserved quantity. Okay. So what is UIJ is basically my that can have, that is X is JX, right? So it can have two. So this is also no, yeah. So this can have values plus minus 1 or plus minus I, right? Plus minus 1 or plus minus I, say. So and this is conserved. So for a Hamiltonian, if I for a Hamiltonian for a given energy, my UIJs are fixed. Say I am fixing it at plus 1 for everyone. So this whole thing, I can consider, I can write it as a new Hamiltonian that is a functional of U and acting as Cj and Ci. It is similar like C, where H U psi, where psi is equal to C1, C2, C3 acting on some zero state. Because there is a sum. So you
Ritwika, when you said it's a plus minus 1, you meant that UIJ and Hamiltonian will have a common eigenstate, but the eigenvalue of UIJ would be plus minus 1.
common.
Do you mean that? Because they are commuting, so
Yeah,
that
they
means
are
they will have
commuting.
common
They
eigenstate,
will
right?
have common. Yes, they will have common eigenstates, but eigenvalues are different. So
Eigenvalues corresponding to UIJ would be plus minus 1. That's what you mean.
yeah.
Okay.
So they can have any values plus 1 and minus 1. So this, for a particular Hamiltonian, this will be my fixed UIJs will be fixed at a value say plus 1 for some
It's
link.
like, almost like parity.
Yeah, you can consider it like that. For every link, there is a specific value, and that value is constant with time. Okay, so then you can thought it like there is a hopping from J to I with hopping strength H of U. My whole
Ritwika, just one. I think one point you should also perhaps you guys are saying the same thing, but if you were to take your origin, the Hamiltonian that you have written on the top of this page, the H term, in that if you did a mean field decomposition, the way I was looking at it, then you could get a one-body Hamiltonian like the same hopping Hamiltonian, but then the things that you have written in bracket would be treated as mean field variables.
Yeah.
But the crucial point here is this is not what Kiteav does, and that's the point of the Kiteav model. That if you write the Hamiltonian in this form that it is written, the terms in the brackets automatically commute with the Hamiltonian, and those remain conserved. Okay, because they remain conserved, I can treat them as constants. just like mean field theory, but a mean field theory would have been an approximation.
Approximation.
Here the statement is an exact statement, and that's why, you know, all this hoopla about saying Kiteav model is exactly solvable is because of this. See, now the problem becomes a one-body problem where without doing any mean field decomposition. So think of Swagatam. This might so if you take a 4 fermion interaction, the kind of things you do. If you could write a Hamiltonian which commutes with let's say C dagger ICI, okay, then you can treat that as a constant.
Okay.
Okay, so it's in that spirit. Perhaps that example gave is not a very good example because it's a non-trivial thing, right? You are saying a site under the Hamiltonian, the number fluctuation Ni remains conserved, but it never remains conserved, right? Because the charges fluctuate. So Kiteav constructed a model by doing this mapping that indeed there are certain hidden conserved quantities which remain conserved on the bonds. Because if you think of spins, the spins in the real problem will keep on fluctuating. Singlet, triplet, pata nahi kya bana diya, right? So there is nothing conserved between two bonds in the spin problem. But if you cast everything in this language, it indeed turns out that certain things in this representation is conserved. Okay, and the problem can be solved in this representation. That's the whole point of the exact solvability of the Kiteav.
Yes, so in the line of thought of this mean field construction, if you so you need to club two operators, right? Suppose you consider the first one with x and x. Now the thing is, if you club I and j and consider it as mean fields, then it would be a different story. But as if you club the xx thing,
I mean, so this is correct. I mean, so if you do
so if ij doesn't commute, that means we need to still diagonalize it.
No, you can do the problem, but then it's first of all, two things will happen. One, you have to solve it numerically, I presume, or within some variational or minimization calculation. Secondly, whatever answer you will get will not be an exact answer.
No, that it will not be.
No. But this is the whole point of Kiteav's thing is that you get an exact solution for the quantum spin problem.
Exactly.
That is the whole point of all of this.
So what I just wanted to point out that if we treat the CCs as a mean fields, it would be a different story, and if we treat the CX as a mean field, it would be a different story.
Yeah, that is true. That is all right. You are using different things as mean fields, but even if you choose the
if we choose the CCs as a mean field, then already CX that thing is already commuting with the thing, so it would be already diagonalized. So
no, what do you mean diagonalized? You have to still know what the CCs are, right? You will not know. So,
if it is commuting,
no, but the mean fields are still not known. Eh? The matrix will not commute because the matrix is made out of the mean fields. The operator just give you the position where it sits.
Yeah. So it was wrong.
No, that's okay. But, okay. Go ahead.
Okay. Another thing I wanted to show is like our placket operator that I defined previously. So if you cast it in this CICJ, so it will simply become IJ, where IJ all are in of the placket sides, then IJ alpha. You can write the whole where my alpha previously where when I have these bonds, so my outer bond which is outside the placket, that one was that sigmas I was considering. So in U, the U will be when I and J is there, this alpha I am talking about, this alpha. Okay, so so my whole BP I can write it as product of this. So one conserved quantity as product of other conserved quantities. So this is another important thing. Okay. Then okay.
Are you going to write down a solution?
Yeah.
Okay.
Okay. So now I want to discuss.
Go ahead, discuss. Just give us.
Okay. So this is one thing that I will use after some time. So another thing is my Hilbert space. Okay. So what was happening in my Hilbert space? So previously, if I have n sides, so 2 to the power n was my total number of Hilbert space or Fock space, you say, right? So now after each side has enlarged from 2 to 4. So my Hilbert space has become 4 to the power n. Okay. So, but if this 4 to the power n has some internal block diagonal structure. Okay, the Hilbert space or the Hamiltonian. Okay. So, how one can understand this?
No, Ritika, sorry, I got confused. Hold on for a second. So,
Yeah.
no. So, okay, what is the confusion? The confusion is you already use this BP, not BP. The fact. Oh, okay. You have simply. No. Okay, let me ask this question. This I missed. When you define this product of the three sigmas as times capital I identity, and that could differentiate between physical and unphysical.
Unphysical states, yeah.
You have not used it.
No.
Okay, then I'm fine. Okay, good.
Okay. Then my physical is Hilbert space is now of dimension 4 to the power n. So now I have this n Majorana in Majorana Hilbert space, if I say in Majorana, no, inside Hilbert space. So there will be each side has 3 bonds, right? And all the 3 bonds have half of contribution of each side. So each side has 3/2 contribution to each bond. Is it okay? So each side has 3 bonds. So that's why 3. And for each bond there is half of the contribution of his own. So that's why 3/2. So my total number of type of bonds will be 3n/3. Total number of bonds will be 3n/2.
Maybe can you just, so what is that you're trying, so I understand that the spin problem was 2 to the power n and you have gone to 4 to the power n.
Yeah.
And then what are you trying, this might be, what you said is fine, but
Yeah.
why are you saying this? Where are you going with this?
I want to say that this 4 to the power n has internal structure of block diagonal of dimension 2 to the power 3n/2.
Okay, fine, good.
So that is the total number of bonds.
So one moment. So which means that you have on each side you have a 1 up and 1 down. So this is 2, and that will be shared by 3 bonds.
No, I'm saying that yeah, you can think of like that also, but I was just saying simpler thing that each side has 3 bonds. Okay, so number of bonds is total 3n, but there is double counting because each bond is shared by 2 particles. So there is half double number. If I consider only 3n, so I am double counting each bond. So n is the side number, right? So if I simply 3 into n, so 3 into n means each bond for this side one time I am considering this bond, for this side another time. So each bond is considered 2 times for 3n. So that's why I am dividing by 2.
Okay. Yeah.
Okay. So that's why my if the 3n/2 is my bond, total number of bonds. So I have 3n/2 number of, yeah, yes.
So 4 to the power n, that's kind of understood.
Yeah.
So what you are saying is that so in general, when we have this kind of bonds to construct the Hamiltonian matrix, you still need 4 to the power n states.
4
But
to the power
within
n
that
cross 4 to the power n states, yeah.
4 to the power n cross 4 to the power n.
Hmm.
But within that matrix, there will be it will be a sparse matrix, probably lots of bonds because bonds
Yeah.
being shared.
Yeah.
So, but then, so that means there will be much more number of zeros.
Yeah.
Uh,
Yes.
ये 2 to the power 3n by 2 कैसे लिखा है?
2 to the power. I have not come to 2 to the
No,
power.
okay, so Ritika, you go ahead. Swagatam, the point is, it's not so much about the sparseness of the matrix, it's about the block diagonal nature. See, if you take any problem, any physics problem, in the sense, a Hamiltonian problem, quantum mechanics, and if you had as many, there's nothing to do with this calculation. If you have a general quantum mechanical problem where there are as many symmetries of the problem as the number of degrees of freedom, you can get to a block diagonal form where the block diagonal size is 1 cross 1 matrix, which means you can diagonalize the problem just by symmetry without having to ever diagonalize anything. Okay. So now the point is, she's using the same argument here, that well, I had a 2 to the power n state Hilbert space gone to a 4 to the power n Hilbert space. So on the face of it, it looks bad, but in doing so, it turns out that there are block diagonal forms because of these added Uij symmetries or the BP symmetries that will construct block diagonals which is much smaller. So diagonalizing the many body problems becomes diagonalizing much smaller.
Okay.
Prabhakar,
I got
think along
the
these lines.
idea. Just I wanted to know about the number. That
No, she will
the
explain.
block size will.
Hold on,
Okay.
she'll explain the number. Since you asked about symmetry and was worrying about sparseness, I'm saying sparseness is not the issue. It's the
Not
block
the issue.
diagonal.
The
Block diagonal thing you should keep in mind. As to the number, she'll explain.
Okay.
Sure.
So 3n by 2 is the number of bonds in my system I have. So how many Uij independent values are there in a system is equal to 3n by 2, right? Independent values of Uij alpha is equal to number of bonds, because in each bond I have a Uij alpha. Is it clear?
Yeah.
Yes. Yeah.
That's the number of bonds.
Yeah. So for a configuration of U, say I am considering a single configuration of U, so U can have two values, +1 and -1. Yeah. So I have two. For
Yeah,
each
got it.
U.
Got
So
it. Got it.
that's why 2 to the power 3n by 2 is my one for one configuration, that my Hamiltonian will have 2 to the power 3n by 2 plus 2 to the power 3n by 2
Yeah.
block diagonal forms.
Yeah.
Okay.
Yeah. Thanks.
Yeah. So that is one thing. And another thing is like, so for each configuration, so how much?
Ritika, I mean, maybe Swagatam got it, but for the others, so explain a bit what, I mean, okay, you said that, I think the point that perhaps needs a little stressing is that given a configuration of UIJs, we have to discuss how you got the UIJs, but let's say you get a configuration of UIJs, which is plus and minus 1, which you distribute on the lattice, and for a given such configuration, you have a 3n by 2 matrix, 2 to the power 3n by 2.
Yes.
And then the total Hamiltonian, however, the total space is still 4 to the power n.
4 to the power n, yes.
So what do you mean by, so what is the structure? Is it direct sum structure, direct product structure? I believe direct sum, is it?
That is direct sum structure.
So there will be a direct sum of how many such sectors are there?
2 to the power n by 2 number of sectors are there.
Because the total has to be 4 to the
4
power
to
n.
the power n, yeah.
Okay, good. So now these many sectors are there, each of them are block diagonal. And what you meant by configuration is the distribution of the UIJs.
UIJs, yeah.
We still need to understand where you get the UIJs from, but we'll come to it.
And now I am first look for the ground state solution. So for ground state, now the question is my energy, on which I have two conserved quantities like BP and Uij alphas. The two type of conserved quantities, but on which my energy will depend. So in my actual problem, the BP was my conserved quantities. So simply, and one can show that if I have a, as this product is defined as BP, so if I consider all these things are as plus uij's, all the links are plus, then I have BP is equal to +1, because product of all these numbers. But if I consider any two minus, then also I will get BP is equal to plus
Ritika, yeah, I mean the argument is fine. I'm just, so this pluses and minuses, why are you drawing it on the vertices and
oh
not?
no, not on the bonds. These are on the bonds.
So you should draw on the bonds, because yeah, otherwise it's a bit misleading. I see. Draw on the bonds and then yeah. And then you're saying, what is the statement if two of them are negative?
Negative also BP will be for this
Even
placket,
them being negative. Yeah.
that will be. But if I have another adjacent things, right?
I see.
So for them,
Yeah.
one bond become minus. So there, but from here there will be one minus. Here there will be one minus. So that will become again. If I sum all the BPs, so that then it will not change.
Correct.
So that's why my UIJs cannot define my energy. My energy will not depend on the UIJs. That will depend on the BPs.
No, this is an argument you gave about the BPs themselves.
Yeah.
Right.
Because many different configuration I can get for but that will have same BP, so that will lead.
Understand the argument. I'm just saying, is there a multiplicity that one can see that
UIJ has different multiplicity for same energies.
For the same BPs.
So for same BPs, yeah.
Which would translate into same energies.
Same energies, yes. So that is being said. So there is a theorem called Leib's theorem. So that says that if you consider all the BPs is equal to +1, then that will lead to my ground state energy. So I don't have the proof.
No, not the proof. What is the statement?
The statement is if I choose all
BP, that is fine. That is
uniform.
Not, is the result.
Yeah.
When asked for a statement of the theorem, means what are the conditions? This might be true, but it's true when, under which conditions? Does it put any what is the exact statement? Do you have it with you? You can read out if you want.
Exact statement.
If you have it on your close to you, otherwise let go.
Okay. I don't have now. Actually.
Okay, so we will discuss this. So because we need to know. Okay, go ahead.
Yeah. So for that, there is a convenient choice that I can take all Uij alphas as +1. That is a convenient choice. For that, this thing has numerically checked by Kiteav that this BP is equal to +1 gives the ground state energy, and Uij is equal to +1 is the convenient choice that was chosen by Kiteav himself. Okay. So then I will move. Then my Hamiltonian has become like x jx I cj plus jy ci plus jz I ci cj. It has become like this simple form. Okay. Now I will go to Fourier. Okay, so another thing is like when I draw this hexagonal thing in my first page, then I constructed this thing. this thing has two sublattices A and B. They are like this, and then I do the translation along A1 to this basis vectors A1 and A2. Then I generated A1. A2 is like this vector, and A1 is my this vector. I generated the whole lattice by this, the two. Okay, have I done something? Yeah, I think. Okay. From here, this is my A2 and this is my A1. Sorry. Okay. Okay. So from here, I generated this whole matrix. So I now go to the Fourier space. After going to Fourier space, my Hamiltonian will look like my A and 2, B and 2 are two sublattices. So Ka Jx to the power minus Ik plus Jy to the power minus Ik plus Jz. Because Jz, there will be no Ik's because these two are belongs to same A and B from same side, same sublattice.
Ritika,
Yeah.
when in the unit cell you will have 3 hanging bonds.
In the unit cell,
What you are repeating, it will have 3 hanging bonds.
this is my basis. Then
Go to the that thing, that picture you had.
yeah.
Yeah, this there you said if you repeat this unit cell, you get the whole matrix. That's what I'm asking. If, at the origin of A1, A2, how many hanging bonds you are considering?
Two, right? This two, because this is the part of this same. These are two different sublattices. So say one sublattice will have 2 bonds. Okay.
Okay.
Okay. So from this one, I will get this Hamiltonian, and after solving. Okay, after solving this, my CK A, CK B will become 1 by 2 of this K minus V of K 1 and 1 on eta K psi K basis, where Vk is equal to I of this whole thing I am saying as Fk, I Fk by mod of Fk, and eta and xi are the diagonal basis, where I can write H as some constant, that is factor of K into eta K dagger, eta K minus psi K dagger psi K. So then it gives me the ground state solution exactly from the whole problem. So this is in K space. Okay. So here the formal.
So Ritika, one quick question. So in whatever you studied so far, is if you are not worried about getting to the lowest energies ground, let's say the ground state, is there any constraint on the use, or they're completely arbitrary?
They are completely arbitrary actually.
Okay. No, the reason I ask this is maybe you can say in terms of what you want to do. Suppose you wanted to solve the Kiteav model using Monte Carlo, what would you do?
At finite temperature, say, then I will choose my different configurations of UI, the configurations which will give distinct BP values, that I will only consider and calculate my energy and then thermalize it. I will proceed by this for a given temperature.
This people have done already. I mean, this.
Yeah.
orthotorofda, etc. I have already
Yeah,
with the Monte Carlo because it's kind of trivial, right? I mean, one thing
yeah.
to get a configuration of the C of the U's, which are the C numbers. Uh, okay.
And actually, from this solution, there are two kind of states. One can get there. One is gapless and one is gapped state. So when my Jx, okay, say I will prove that. Okay, my fk was equal to jz plus jx to the power minus ik plus jy to the power minus ik. It was like that. So that when it will give me the zero band gap solution, when my jx mod plus jy mod is greater than equal to jz mod, then I will get my this kind of bands. And for any two, this can be x and y, this can be yz and x, this can be zx and y. So if all the three satisfies, then I will get this kind of band structure where E will be proportional to K near this point, and if this condition is not satisfied, then my E will be proportional to K square near the minima, where Jx mod plus Jy mod is less than Jz mod. For that I will get gapped states. And these two states are connected by phase transition, but this phase transition is not happened by symmetry breaking, because as you can see that these are Majorana excitations, not real excitation or hopping thing. So no symmetry is getting broken. So there is a internal topological order which is getting changed, that I don't know very explicitly. And the other conclusions are like, then one can in that paper I have reviewed, there they considered some correlation, magnetic correlations, and they showed that they have only short range correlations. So this kind of states we can represent as spin liquid states, okay, with average magnetization 0.
So Ritika, I think I mean, instead of going into further other things, because it's anyway 5, I think the thing maybe you should comment a bit more is this thing that you have started right now by saying, see, all of this is done in the sort of mapped space so far. When you say now the real excitations are in the real space, what is happening? So that is what the question is.
So so I have to now map to my actual state, right? So my di is di was defined as sigma x into sigma z. So I can multiply it by, say, a factor I minus I sigma x I sigma y I sigma z I.
So just hold on, Ritika. Sorry, I'm sorry to interrupt because I already said you to say something, and then I'm taking you back. Just remind me, where did you use the constraint in this calculation? The
constraint of physical and physical state?
Yes.
No, I haven't used.
But then how do you know the answers are correct? How do you know the answers are correct?
This up till now, what I have got in my extended space.
Yes.
So in extended space, there is no physical and physical. Now I have to come back to my actual space.
Okay. So you are going to do it now.
Yeah.
Okay.
So then my di is defined. So I will define my projection operator, total projection operator, as product of each side's projection operator, that is defined as 1 plus di by 2, product of I is the site index, site. So what it will do is like that, when my 0 state will be there, this di will be 1. So 1 plus 1 by 2 is 1. So 0 0 and for 1 1 state, and for other state it will be 0 0 1 and 1 0 state. So this is my projection operator, but the interesting thing is like this total projection operator commutes with my Hamiltonian. So exactly whatever I got this spectrum, that will be just translated to my actual problem. So I don't have to do anything.
No. What do you mean? No. The P commutes with H, yes.
Yeah.
But then what did But then the P has 0 and 1 eigenvalues on physical and non-physical, I presume.
Yeah. So for the one physical states, whatever my H will be, H spectrum will be that I will only consider.
So you'll throw away part. You
Yeah.
use the P to select physical and non-physical states, right?
Yes.
Yeah, so this is what we were talking in the beginning, right?
Yes,
So the D by itself doesn't tell you, it's the P which has to act on the entire spectrum.
Entire spectrum.
And
Yeah.
the P commutes with H, and this is what I was saying. I mean, these people do in slave spin also, or slave rotor also. You could, if you want to put the constraint, so far as what these guys have been doing, slave rotor and slave spin, we have put constraint on an average. This is an exact statement. This is not an average.
No.
So even there, you could construct an operator that commutes with the Hamiltonian, much like me, exactly the way you have done, which commutes and then tells you what is physical, what is not physical.
Yeah.
Okay. The good thing about this problem is that the total problem is exactly solved. I mean, that doesn't happen in the slave rotor or the slave spin. So you're still left with the money body problem there.
Okay. So I am finished.
You are done. So
Yeah.
maybe you can tell in a few words what you want to do with this. I mean, you have studied this model, which is good. You have also appreciated what are the conserved quantities, what can be done on a Monte Carlo. So what is that you want to do? I mean, this is all done. By 2019 or 20, all of this finite temperature was done.
Yeah.
So you want to comment on this time or next time if you have any here?
I'm not.
Okay.
I will comment next.
We'll reserve it for next time.
Yeah.
Shubhajyoti.
Yes, sir.